Okay, the next situation we're given, we have a 40 microcoulomb charge separated between the two plates. That is, we got 40 microcoulombs in each plate of a 9 microfarad capacitor. And we want to figure out how much energy it takes to move the next microcoulomb of charge. So, first thing we do is, if we know the charge and the capacitance, since capacitance, a farad is a coulomb per volt, capacitance is your charge divided by your voltage. 9 microfarads then is 9 microcoulombs per volt. We can use a formula, but we can just reason this out very easily if we know what the units are. If we've got 40 microcoulombs and 9 microcoulombs for every volt, that means we're going to have 40/9 of a coulomb, 40/9 of a volt. Now we can do that. We can divide the 40 microcoulombs by the 9 microcoulombs per volt, and we get 4.4, 4 repeats, but we're going to just use the approximation, 4.4 volts. And we note that a volt is a joule per coulomb, so this is 4.4 joules per coulomb. Now we want to know the work to transfer 1 microcoulomb. Well, that's fairly easy. Right now the voltage is 4.4 joules per coulomb, so the approximate work is going to be 1 microcoulomb times 4.4 joules per coulomb, or 4.4 microjoules. Now this is approximate. The voltage is actually going to go up because the charge goes up by 1 coulomb. That's 1/40th of the original charge. That's 2.5%. So the voltage would actually go up 2.5% on this transfer. So the average voltage would be half of the 2.5%, very roughly. A pretty good approximation here, or 1.25% greater than this, which would get you up to around 4.5 volts. In other words, this would round off to 4.5 volts. Your result would be pretty close to 4.5 volts. And so you maybe want to use an in-between voltage to get a more accurate approximation. However, we're going to look at the integral. So first thing we want to understand, though, is if you know the charge and the capacitance, you can figure out the voltage. And then if you know how much, what small amount of charge you want to transfer, you can use that voltage to approximate the energy required to accomplish the transfer. Now we're going to symbolize this and try to figure out how much energy it takes to charge up the capacitor from the uncharged state. And then we're actually going to use that to calculate the energy per unit of area in this between these capacitor plates. Now we'll talk about that just a little more after we do the calculation. We're going to call that the energy density of the electric field between these two plates.